Good afternoon to everyone. Welcome to one more session of DBMS. Welcome back. Welcome to the gate gate through questions. Welcome back. Welcome to the gate gate through questions. Yeah, sorry. So this is Ravi Kumar. I'm working for MedEasy since last 12 years. Sorry for the delay of 6-7 minutes because of some technical issue. So hope you all doing good. So we are really missing you. So hope you all doing good for your preparation and everything is set for the preparation. So keep revise the subjects and keep give full syllabus tests. So almost daily one test. So today we are going to discuss some of the concept oriented and some are simple, some are difficult, but try to collect the maximum concept oriented questions. Okay, so welcome back. Good afternoon to everyone. Right. So let's move to the question. See this question. Consider given relational schema R with n attributes. Which of the given statements is are true? Multiple selection question. So maximum 2 power n minus 1 possible super keys in relation R. So maximum n possible candidate keys in relation R. Maximum n by 2 possible candidate keys in relation R. Maximum n factorial possible super keys in relation R. So it's easy question only, make it fast. So please answer the answer to this question in your comment box. Right. Sombit Nag Chaudhary Pandey. Right. Okay. So see, total n attributes in the relation R. Okay, let's see the possibility of candidate keys first. If I take one attribute is a candidate key, total NC1 candidate keys. Okay, so A1 itself is one candidate key, A2 one candidate key, and A3 is one candidate key, and so on. Okay, if two attributes if we consider as a candidate key, okay, then total possibilities are NC2 candidate keys. Okay, so A1 A2, okay, like this, total NC2 candidate keys. If three attributes if we consider as a candidate keys, then total it is NC3 candidate keys. Okay. So similarly, if NC n by 2 attributes act as a candidate key, out of n attributes, every n by 2 attributes act as a candidate key. Total candidate keys are NC n by 2. So if n attributes combinedly considered as one candidate key, then it is NCN candidate keys, means one candidate key. Okay. So, but if one attribute is a candidate key, two attributes is definitely not a key. If two attributes is a candidate key, one attribute is not minimal, means not a candidate key, right? So when we consider a candidate key, we can consider any one of this set. We can consider any one of this set. So he is asking maximum possibility. So maximum possibility from NC1 to NCN, all these terms. So this NCN by 2 is becomes maximum term. Okay, this NC n by 2 is the maximum term. So this can be the maximum possibility of candidate keys in a relation. Okay, so and if we consider super keys, if each attribute forms the super key, if each attribute forms the candidate key, then one attribute is a candidate key, means two attributes is a super key, three attributes is a super key, and all n attributes is also super key. And total maximum possible super keys can be 2 power n minus 1, okay, is the maximum possible super keys under assumption, okay, each single attribute is a candidate key. So so the maximum possible super keys of the relation can be 2 power n minus 1, and maximum possible candidate keys at any moment of time is nc n by 2. Okay, right? So it's also one more similar extension question. Consider given relational schema with n attributes, a1 to an n attributes. So how many super keys are possible if every possible n minus 1 attribute forms the candidate key? So if every possible n minus 1 attribute if forms the candidate key, then total how many super keys are possible? Right? Mohit Sharma n plus 1, Naik n, Ansuya n, Nikhil, all are saying n. Devanshu n plus 1. See, again it is similar to the previous. Okay, see, out of n attributes, okay, every possible n minus 1 attributes, that means nc n minus 1, okay, so these are the total possible candidate keys. Okay, these are the total possible candidate keys. Okay, if n minus 1 attributes, assume that if the relation have some four attributes, if we assume that a b c d, so if three attributes like a b c, okay, so b c d and so on, so if three attributes, that is 4c2 4c3, okay, so these are the 4 candidate keys. But if three attribute itself is forms the candidate key, then all 4 attributes is not a candidate key, but it is also one of the super key. So this is one of them. So this is one more super key. So the candidate keys is also super keys, and this one extra super key which is not a candidate key, total it become 5. So it means that if n minus 1 attribute forms the candidate key, then all n attributes, okay, so means if we select all n attributes, ncn means one selection, so this is also becomes a super key. So candidate key is also super key, and this is also super key, and total possible super keys are becomes, okay, so nc n minus 1 plus ncn, so nc n minus 1 is n plus 1 is the total possible super keys. Okay. So in case if we say nc n minus 2 attributes is a if we assume that n minus 2 attribute forms the candidate key, then you will extend the same way. Okay, you will extend the same way. So out NC n minus 2, NC n minus 2 candidate keys. Okay, n minus 2 attribute forms the candidate key, means superset of that. It means more than n minus 2 attributes. N minus 1 attributes also forms the super key, and n minus n attributes also forms the super key. All these you can add it. Okay, so this is what we done in the previous question also. So see, by chance if nc1 candidate keys are there, okay, if nc1 candidate keys are there, if one attribute is forms the candidate key, if one attribute is forms the candidate key, then all these are become super key sets. Okay, that's why total possible super keys are becoming 2 power n minus 1, right? So hope you cleared this question. Right. Now let's move one more question which is related to the foreign key. Okay. So this question related to referencing and reference relation. Okay, foreign key and the referencing attribute and referenced attribute, relationship between them. Okay, so please read the question. So which is true regarding foreign key? Each record of a referencing relation related to exactly one record of reference relation. Each record of referencing relation related to at most one record of a reference relation. Each record of a reference relation related to some records. Okay, so so at least one. You can say one or more. Okay, then next option, each record of a reference relation related to many, 0 or more. Right. Saurya, Bose, Nikhil, Anshu, Abhishek, Rajiv. Yeah, many are answered correct. Subhashini. Okay. See, the relationship between a referenced and the table which contain primary key which is referred by some foreign key. Assume relation R with A is the primary key. Okay, so relation R with A is the primary key and relation S D is a primary key, and assume that C foreign key referencing to this relation R. Okay, so let's say this is the foreign key constraint. Okay. Now the table which contain foreign key we call reference relation, and other relation the primary key which is referred by the foreign key is reference relation. Okay, so foreign key can consist null. Foreign key can consist null. So the referencing relation whose foreign key value is null, this kind of referencing record is out of foreign key constraint. Okay, it is not related to any of the reference table. Okay, so even if it by chance the referenced key is alternative key, even by chance null here, okay, if it is alternative key, if this A is alternative key, let's say C is a primary key, C is a primary key, A alternative key, then the foreign key can refers to alternative key also. Even if you have null in the reference table, still this null not refers to this. Okay, so the null record of the foreign key values is out of foreign key references. So other than that, okay, each referencing relation are related to one record of the reference table. Each referencing relation, it seems to be one to many mapping. Okay, so even though it is one to many mapping, it need not be exactly one from the referencing to referenced. Okay, so because of this foreign key value null, and so not every record of the reference table can related by the foreign key. Okay, so zero mapping is allowed in both the sides, one to many mapping. So some record of reference table may not related to anyone, and some record whose foreign key value is null from the referencing relation may not related to anyone. Okay, so in this way, so we can say that each record of the reference relation can relate it to zero or more records of a referencing relation, and each record of the referencing relation can relate it to, okay, so at most zero or one record because of this null value, zero or one record of the referencing relation. So this is the explanation related to the here we are saying zero because of the foreign key value can have null value, those are out of referential constraint, right? So so correct answer to this given question. So each record of the referencing relation can relate it to at most one, okay, zero or one record, okay, at most one a record of the reference relation, and each record of the reference relation can relate it to many records of the referencing relation, right? So B and D is correct answers. Right. Okay, so so let's move to the ER model question. So one frequent model question from ER diagram, so finding minimum relational tables, for the given ER diagram. Okay, so roughly write the diagram and I will share this PDF notes. Okay, so I will share this PDF notes in groups or wherever it is possible. Okay, so just roughly write the diagram and solve the problem. Okay, so here one-to-one mapping with total participation and one-to-many mapping. Okay, so this is many-to-one mapping, one-to-one mapping with partial participation both sides, self-referential one-to-many, self-referential one-to-one, and this is many-to-many. R7 is the many-to-many mapping. Prandi, Sam, Pintu, Komal Kumari, Anshu, Rishabh. Very good. Okay. So hope you remember the how to minimize for general ER diagram. Okay, so 10 different rules we discussed. Okay, so just recollect it once. If one to many mapping, either partial participation or total participation, either partial participation or total participation, a relationship can combine to the right side entity. Okay, one to many mapping, either partial participation at the right side or total participation at the right side. Both these cases, the relationship combine to the right side, many side entity set. Okay, so E2 and relationship can combine into one RDBMS table. So in this scenario, we are assuming this left side, E1 side of one to many is partial participation. So if this left side is total participation, what to do we'll discuss separately in one other question. Sorry. So one to many mapping, right side either partial participation or total participation, a relationship can combine with E2. Then next, many to many mapping, partial participation at both sides. Okay, many to many mapping, partial participation at both sides. Okay, if it is the scenario, the relationship should be separate. Okay, a relationship should be separate and AC combinedly is become key. Okay, so if it is one to one mapping, if partial participation both sides, then a relationship can combine either with E1 or with E2. Okay, so but one minimum two tables only. Okay, so either E1 in one table and relationship with E2 in other table, or E1 relationship in one RDBMS table, E2 is other RDBMS table. This is the third rule. Next possible minimization. If one to one with at least one total participation, minimum one RDBMS table is required. Right? So same as the case for self-referential. Self-referential one to many can combine with the entity set. Self-referential one to one can combine with the entity set. But if self-referential many to many, okay, should be separate table. Okay, weak entity set. Okay, if weak entity set is exist, relationship and weak entity set should be one table and E1 should be the other table. These are the 10 different rules. Okay, so just recollect all these 10 different rules. So 90% of ER model questions you can able to solve just by analyzing these 10 points, right? So then in this 10 rules, okay, two things are missed. Those two things are one to many, total participation in the left side, how to design, and many to many. Okay, so total participation if exists, how to design, that we will discuss separately in the next question. Okay, so then back to the our ER diagram. See, one to one total participation. So entity sets can be combined together. Okay, so many to one can combine with the many side entity set. So this portion of ER diagram is becomes one RDBMS table. Okay, now one to many relationship can combine with the E2 entity set, and one to one partial participation both sides. Entity sets are not allowed to combine, but relationship can combine with either the sides. Okay, so one to many self-referential also can added into the entity set. So this portion of ER diagram is becomes one more RDBMS table. Okay, so one to one self-referential can combine with the entity set. Okay, so this is one other RDBMS table, and many to many relationship with partial participation both the sides is separate table. Okay, so 1 2 3 4. Okay, so minimum 4 relational tables required. Right? Okay, now so many are asking about this. So see this one. For example, one to many mapping. Okay, total participation in the left side. Okay, total participation in the left side. In this case, then total how many minimum RDBMS tables required? Okay, so one question, how many minimum relational tables required which satisfy 1NF? And second question, how many minimum relational tables required which satisfy BCNF? Right? How we get grouped R2? So so yeah, so one to one total participation both sides. Okay, so the same thing explained in one separate case, just recollect this one. So one to one with at least one total participation. Because of this total participation, even if entity sets are combined into single table, okay, even all these entity sets E1 E2 entity sets combines into single table, still it not going to be lose any constraint. Okay, so A is act as alternative key and C is act as primary key, and minimum it required one RDBMS table and no need of any foreign keys. Okay, so this scenario, so one to one mapping with total participation one of the side, either left side or both the sides. Okay, if total participation at least in one side, then entity set can combine into one single table. Okay, so the same scenario happen in this relationship of the previous question R2. Okay, next, so what is the answer to this question? How many minimum relational tables required which satisfy 1NF? It is one to many. Okay, so irrespective of the right side participation, a relationship can combine with the E2. But the left side, if it is total participation, okay, the left side entity set, if it is total participation, then what we can do? Right, many are giving like 2, or some are given 1. Okay, see, irrespective of the participation, if one to many mapping, a relationship can combine with E2. Okay, so even total participation or partial participation, a relationship can combine with E2. So but we didn't merge E1 into the same table because of the partial participation in the previous question. So if it is total participation, the whole thing can combine into one single table. Okay, so let me write the FDs, functional dependencies. Okay, so functional dependency of the E1 is A determines B, and functional dependency of E2 C determines D. Because of one to many mapping, C is a key, so functional dependencies of this one is C determines A. Okay, so if one to many mapping, total participation in the left side. Okay, so we can combine into one single table. So like E1 relationship E2 can combine into one single table, so which is attributes A, B, C, D, and dependencies are C determines D as well as C determines A, these two FDs, and A determines the B. Okay, so again C is become primary key. So now it is okay for the 1NF. Okay, it is okay for the first normal form, and it is also in second normal form because simple key, no partial dependencies are occurred. Okay, it is okay for 1NF as well as second normal form is also satisfied. Okay, but this relation, this design, okay, not 3NF as well as BCNF. Not BCNF also. So so means it, if not BCNF, not 3NF, means this FD is forms the redundancy. Okay, so in order to avoid this redundancy, again we need to decompose into two tables, like the E1 entity set attributes AB with A is the primary key should be in one table, and E2 and relationship, okay, E2 along with the relationship, okay, this is E1 data, so is in other table as like the previous design. So now C determines DA is becomes other table. Okay, if we take minimum two tables, now it is 3NF is also okay as well as BCNF also okay. So many many are asking, so what happened in the total participation? See, the possibility of asking this 1NF design is very means almost very not that much frequent in the examination, because minimum one table is fine, but it is violate the BCNF. If violate the BCNF, it forms the data redundancy. Okay, generally whenever they say convert into RDBMS, they may not expect some design which has lot of redundancy. Okay, so that is the reason. So examination point of view, this two table design which satisfy for BCNF is only more frequent. Okay, so very rarely they use it to ask like this. In case if they say 1NF is sufficient, then how many minimum tables required? Then definitely answer should be one only. But if you say BCNF or 3NF, then minimum it required the two tables. Okay, so if one to many, left side partial participation, right side either total or partial, minimum two tables. Okay, if one to many, left side is also total participation, left side is also total participation, then minimum one table, but it is only for 1NF, again minimum two table for 3NF as well as BCNF, right? So this is the one extra special case. Okay, so one to many relationship with total participation in the left side. Okay, similarly same question. Previously we discussed many to many partial participation both sides. Now if many to many total participation in one of the side, either total participation left side or total participation right side or total participation both the sides, then minimum how many tables? Just recollect it once, previous question. So previous to previous question. So many to many, partial participation both sides, then minimum three tables. If one of the side total participation, then how many relational tables required? Right. Yeah. So I'm going little fast here. So I think many are already answered. Okay. If if many to many, if partial participation both side, then relationship should be separate. If one of the total participation exists, so even if we combine the total participation side, so it's not going to be cause any violation to the participation, but still the design is not efficient, okay, because it is forms the data redundancy. Okay, assume E1 relationship is combines together, so ABC, but here the FD ABCE because of this extraneous attribute E. Okay, ABE, sorry, not C, ABE. Okay, so ABE, ABCE, okay, ABACE, okay, right. The FDs are only A determines B is one FD and AC determines E is other FD. Then overall candidate key is become AC. If overall candidate key is AC, then A determines B is partial dependency. It is not 2NF. Okay. So now it is only in 1NF. Minimum 2 tables is required, but the design is only for 1NF. Okay. So this is only satisfy for 1NF. For 1NF, minimum 2 tables. Okay. But if you want 2NF or 3NF as well as BCNF, you have to decompose further. So in that case, so E1 entity set AB should be separate and relationship ACE should be separate and E2 entity set CD attributes should be separate. Then so minimum, okay, so 2NF or okay, 3NF or BCNF. Okay, minimum 3 tables required. Right? So if this also frequently used to ask by the many of the students through WhatsApp and all. So many to many total participation if both sides, many to many total participation if both sides, then minimum 1 table is sufficient. Many to many total participation if both sides, minimum 1 table is sufficient, but it violates for the BCNF. Okay, so then FDs are A determines B from the E1, C determines D from the E2, and AC determines E from the relationship. Okay, AC is become candidate key. So minimum 1 table, but it is A determines B and C determines D partial dependencies. Okay, this is only 1NF but not 2NF. Okay, so minimum 1 relational table required for this. So if you want 2NF or 3NF or BCNF, again it required the 3 tables, either for 2NF or for 3NF or for BCNF. Okay, so minimum 3 tables required. Okay, so that E1 data AB should be one separate table, E2 data CD should be one separate table, and ACE should be one separate table. Okay, so this is the possible design if many to many with total participation is given, right? Okay, so these are the possibility of the questions from ER model. Okay, so solve the question from the queries. Okay, so how many given queries correct representation to retrieve SIDs of the students enrolled for some course taught by Korth and some course taught by Navate. Enroll and course are the RDBMS table. So enroll natural join with course, instructor equal to Korth and instructor equal to Navate. So T1 renames to enroll, T2 renames to course, T3 renames to other course. Sorry. And this join, this conditional join is applied. Okay. Then T1, P1 enroll and course, T2 and P2 enroll and course, and these conditional joins apply. Okay. So out of these three queries, how many queries are correct for retrieving retrieving SIDs enrolled for at least one Korth and at least one Navate? Right. Right. Okay. See this one. So instructor equal to Korth and instructor equal to Navate. So and condition between two different values, okay, for each record. Okay, none of the record will satisfy. So because no record will satisfy here, no record will satisfy here, this result is empty, right? Empty set joins with any other table, result is empty. The query one results empty record set. Okay, it is incorrect query for the given specification. So this is one of the well-known query. Okay, not much to explain. So here T2 is one of the course, whose instructor is Koth. T3 is one of the course whose instructor is Navate. These two conditions can possible to become true. But if it is a Koth course and the T3 is the Navate course, okay, so T2 course ID if equal to T1 course ID, and definitely T3 course ID which is not same as T2 course ID because one is Koth course and other is Navate course. Okay, T2 and T3 courses are different courses. Okay, so two different courses comparing with one course ID of T1. So one of these condition guarantees fail. Okay, one of this condition guarantees fails. This result is also empty. T2 result is also empty. Okay, so in order to prove that, so SID enrolled for some Koth course as well as SID enrolled for some Navate course, it's mandatory that so we need two instances. Okay, we need two instances of enroll and course table. Okay, so here using one instance of enroll and course, we can prove that student enroll for some Koth course, and using one more instance of enroll and course, okay, we can prove that student enroll for some Navate course, and you can take the student who enrolled for Koth course and also should be equal to the student who enrolled for Navate course. Okay, the only third query gives the correct result. Okay, so in order to prove that these kind of queries, okay, so we need two instances of the enroll and course table. Okay, one instance of enroll, one instance of course also fails, and one instance of enroll with two course table also not possible to express, and two enroll and one course also not possible to express. So it required two enroll instances and two course instances, whatever the logic we apply, right? Right. Srijal, are you okay? Thank you. Yeah, I'm okay. So next, one more interesting question. Okay. So enroll relation SID course ID. Look this question. Enroll relation SID and course ID, and course relation course ID is the primary key. So how many given queries correct representation to retrieve SIDs of the students enrolled for, okay, some course enrolled for every course taught by Koth and every course taught by Navate. Okay, answer this question. Every course taught by Koth and every course taught by Navate. Swaroop, thank you. So it's a normal cold only, nothing much. So the question, how many of given queries, like 3 queries are given, it's like a numerical answer. Okay, so numerical type question. How many queries, how many of given queries are correct? Ansuya, Rajesh, Nikhil, Komal Kumari, Subhashini. Think and answer. So 3 queries are given. So requirement is we need to retrieve SIDs of the students. Okay, retrieve SIDs of the students enrolled for every course taught by Koth and every course taught by Navate is the specification. For this specification, how many of given 3 queries are correct? Yes, third query. Okay, assume this is Navate. Right. Yeah. See, instructor equal to Koth and instructor is Navate. Okay, AND operation between two different values. Okay, no single record, none of the record of the course table will satisfy both these conditions. So the result of this denominator set is empty. Okay, if result of the denominator set is empty, okay, for division operation you will get the all SIDs of the enrollment. Okay, this query gives the all distinct SIDs of enrolled relation. Okay, so it is not eliminating the student who are not satisfied this given specification. So the first query is incorrect for the given specification. Okay. So but second, in this case, second and queries works fine. Okay, so here the denominator is, so every Koth course as well as every Navate course IDs. Okay, so the IDs of this denominator, so instructor equal to Koth and our instructor is Navate. Let's say C1 C2 are the Koth courses, C3 C4 are the Navate courses. So if denominator is all 4 courses, then SID which pairs with all the 4 courses are in the result. Okay, so then the SID who enroll for every Koth course as well as every Navate course is in the result. Second one is correct query. And anyhow third one is correct query. There is nothing much to explain in the third one. Okay, so out of 3 queries, so 2 queries are correct for the given specification. Right? Make it fast. See this one, very simple question. Okay, just 2 minutes. Okay, so these are the relation R, some records are there, relation S, some records are there, null value is also there, null is also there in the S relation. Okay, so select star from relation R where B greater than any function is used. Okay, select C from relation S. Second question, select star from relation R where B greater than all function is used here. Select C from relation S. So the how many records in the result of these two queries? Right? Rajan, Rakesh, Komal Kumari, Srijal, Anuj. Yeah. So let's see this one. Any function, R connectivity, okay, R connectivity for all the values of inner query result. Okay, so it behaves like this. B greater than any, B greater than any, these are the set of C values. Set of C values are 5, 4, null and 8. Okay, so B greater than 5 or B greater than 4 or B greater than null or B greater than 8. Okay, so if any R operation means any one of them is satisfied, then result is, then the condition is true. If B value is 15, so 15 greater than so 5 is true. Okay, this record in the result. So B value is 10, 10 greater than 5 and 10 greater than 4 and 10 greater than 8 is also in the result. So if B value is 4, so 4 greater than 5, 4 or 4 greater than null is unknown. Okay, so false are unknown, overall it is unknown, it is also not in the result. And the 10, the 2, B value is 2, 2 greater than none of them, okay, is also not in the result. There is no much twist in this question, so the two records in the result. Okay, but when it comes to the second question, all function behaves like end connectivity between all the values of inner query result. Okay, end connectivity between all the values of inner query result. That means, so B greater than, okay, 5 and B greater than 4 and b greater than null, b greater than null, and b greater than 8. Okay, so whatever the b value, because of this null comparison, okay, is whatever this b, okay, comparing with the null, the result is unknown. Okay, result is unknown, unknown and, okay, true, unknown and false. Okay, both these cases there is no chance to get the result is true. Okay, the result of this expression, either false, okay, or unknown. Result of this expression, either it is false or unknown. There is no chance to get the result is true. Okay, so whatever the b value we consider, so because of this null comparison, and end connectivity, so the result of this where comparison either false or unknown. So no one means result never be true, so no record of the relation r is in the result. Okay, so 0 records are in the result. Right. Now, so highest normal form is not required, just so remaining questions I will give you for the practice. So solve this question. Which of the given relation cannot possible to decompose into BCNF with lossless and dependency preserving decomposition? Which of the given relational schema cannot possible to decompose into BCNF with lossless join and dependency preserving decomposition? Right? Post your comment. Right. Rajesh saying BC. Prince Kumar Sombit. So many are saying option C. Now, see this one. A closure determines ABC, but DE in the relation. So candidate keys for this first FD set. ADE, BDE, CDE are the candidate keys, right? So this given relation in 3NF but not in BCNF. Okay, given relation 3NF but not in BCNF, but can decompose into BCNF. Okay, because of ADE and BDE, CDE are the candidate keys. So the first FD also fails, second FD also fails, third FD also fails. Okay, but because all the three FDs over the ABC attributes. Okay, if ABC in one table, then A, B, C, all three are become candidate keys. Okay, so because of A determines B and B determines C and C determines A, and okay, one of the common attribute can consider as a key. You can take ADE or BDE or CDE. Okay, ADE or BDE or CDE. If you decompose like this, okay. So BCNF lossless join, dependency preserving, all are satisfied. BCNF lossless join, dependency preserving, all are satisfied. Okay, can possible to decompose into BCNF without violating lossless and dependency preservation. Now, if you come to the second one, the candidate keys are AB and BC. Okay, for the second FD set is candidate keys are AB as well as BC, right? So C determines AD is failed for BCNF, D determines E failed for BCNF. Okay, so anyhow D can be separated. Okay, D in one table. Okay, now in case if you take ABC one table and CAD one table, assume that in case if you design like this, still it is not BCNF. Okay, the reason is AB determines C is one FD, here C determines AD is other FD. Okay, but C determines A also comes to the first relation because AC in the same table. So C determines C determines A also in this first table. This first relation again fail for the BCNF. Okay, so again fail for the BCNF. If you decompose further, so like assume that AC in CA in one table and BC is in one table. If you decompose like this, okay, and CA anyhow here is there, and CD can consider as one table, or you can take CAD in one table. Okay, so CD in separate table or CAD in one table. Okay, D in one table. If you decompose like this, then AB determines CFD is lost. Okay, so the second relation, this relation not possible to decompose into BCNF and lossless join and dependency preservation. Dependency preservation guarantees fails. Okay, if we decompose like this, if we decompose like this, BCNF fails. Okay, lossless join is okay, and dependency preservation is okay. If we decompose further, lossless join is okay, dependency preservation fails. Okay, BCNF is okay. Okay, so one of them, either BCNF or dependency preservation, is failed here. Okay, see here C determines A only, but here in the next FD, C also determines the B. It means here AB also key as well as C also key. AB also key as well as C also key. So in this case, so excluding DE, if we decompose like this, okay, ABCD in one table and DE in one table. Okay, then AB determines C is 1FD and C determines ABD. Okay, C determines A as well as C determines D. Okay, so D determines B. Okay, so okay, yeah, ABC in one table, and if you take CD in other table, okay, you can decompose like this. Okay, C determines D comes to here, and D determines E is here, and AB determines the C determines AB also. Okay, so because C determines the A and C determines D and D determines the B, it means C determines the B also. Okay, so C determines AB. So AB is a key as well as C is also a key. So lossless join, dependency preserving, BCNF, all are satisfied for this one. Okay, so lossless join is true, dependency preservation is true, and BCNF is also true. It is also possible to decompose. Now here this is AC one table and BD one table and remaining attributes along with the AD in other table. So if you decompose like this, AC is one table and BD is one table. So B key here and A key here. So ABCD is over, then ABE in one table. ABE in one table. Okay, if we decompose like this, then lossless join, dependency preserving as well as BCNF all will satisfy. So only the second relation unable to decompose into BCNF along with lossless join and dependency preservation. So answer to this question is option B. Right? So let's see the next question. So related to the indexing, a B plus tree of order D is a tree in which each internal node has D and 2D key values. Each internal node has D and 2D key values. Okay, root has between 1 and 2D key values. Okay, so what is maximum minimum number of internal nodes in a B plus tree? Okay, of order 9 and okay 2048 leaves. Okay, solve this question. This is one important model question from the indexing. Okay, so everyone try to solve this question. Okay, right? So at least first try for maximum. So maximum possible internal nodes, and second minimum possible internal nodes. Right. Ansuya. Keep commenting your answers. Right. Okay. So to get the maximum internal nodes, okay, so bulk loading design can be used for this. So bulk loading design can be used for this. So to get the maximum internal nodes, okay, so take the minimum possible occupancy of each node. So total 2048 leaf nodes. Okay, 2048 leaf nodes. Okay, these are the leaf nodes. We need to design with maximum internal nodes. Okay, maximum internal nodes. So maximum internal nodes means take the minimum occupancy. So minimum D keys. Okay, so minimum D keys. So and previous level we need 2048. Okay, 2048 block pointers, right? Previous level we need 2048 block pointers, minimum 9 keys. Okay, so minimum 9 keys means minimum 10 block pointers per node. Okay, minimum 9 keys means 10 block pointers per node. That means 2048, so divide by 10 block pointers per node floor value. Okay, so that means it is 204 nodes at this level. So previous level we need 204 block pointers. 204 block pointers, it means, so 204, and one node can capable minimum 10 block pointers. Okay, so that means 20 floor value, minimum occupancy per node we considering here, we considered here. So 20 nodes. Okay, so 20 block pointers previous level. So 20 block pointers means 2 nodes, and 2 block pointers at the root level. Okay, root may not require to satisfy 10 leaf nodes, 10 block pointers. So root node is 1 node. So this is the maximum possible of internal nodes. Okay, so this is 23 plus 204. So 227, right? 227 is the maximum internal nodes. So any correct answers? So Komal Kumari is given correct answer. Ansuya is given correct answer. Okay. Yes, 227. Srizal. Right. Now, let's come to the internal minimum internal nodes. So then 2048 leaf nodes. Okay, so we need to design B plus tree with minimum internal nodes. Minimum internal nodes means we need to take the maximum filling factor. Okay, so maximum 2D keys. Okay, for root also and for other nodes also, maximum 2D keys. So maximum 2D keys, it means that, so maximum 18 keys. Okay, maximum 18 keys means 19 block pointers max. Okay, each node can have at most 19 block pointers. Okay, so we need 2048 block pointers. So 2048, each node can capable at most 19 block pointers, because we are considering maximum node factor, filling factor of the node. You should take the seal value for this. So 2048 divided by 19, the calculated value, okay, is 108. Okay, the previous level 108 block pointers. So 108 divided by, each node can have at most 19 block pointers. Okay, so 108 divided by 19. So 6 nodes. So previous level 6 block pointers. Okay, 6 block pointers means it is 1 node. Okay, so total 114 plus root node is 1. So total 115 nodes. Right. Prince Kumar Komal. Viral videos is the name. Right. So see this one here, the maximum and minimum is given with respect to keys, but here internal node distribution with respect to pointers. So minimum 9 keys means 10 pointers. So maximum 18 keys means 19 block pointers. Okay, so that is the one small observation. Okay, so that is a place where you may do mistake while you are doing calculations, right? Okay, so answer this question. Which of the following statement is or true? If block size allocated for B tree or B plus tree node is same, if block size is same, okay, if block size allocated for B tree node or B plus tree node is same, then IO cost of B tree index is less than or equal to B plus tree index less than B tree index. So same thing, same option here. So B tree IO cost is less. Okay. Then third option, if order of B tree and B plus tree node is same, degree of the node is if same, okay, then the IO cost of B plus tree is less or IO cost of B tree is less. Recollect this, recollect the concept related to this question. So similar concept we discussed in class. Make it fast. Ranjan, Mansi AD, Komal Kumar BD, Rajesh BC, Ansuya AD, Lavivoma AD. Right. Subhashini, Sugan, Sombit. See this one. If block size which we allocated for B tree or B plus tree node if same, so whereas in B tree node, okay, whereas in B tree node, so assume if P is the number of block pointers, okay, so block pointers also required and record pointers also required, which is P minus 1 record pointers, okay, as well as P minus 1 keys for both internal node and leaf node. Because of more record pointers in the internal node, okay, so the order P value is reduces, order P value is reduces, okay. So if you take the B plus tree node, okay, so for internal node, okay, P block pointers and P minus 1 keys, P block pointers as well as P minus 1 keys, okay, no record pointers. So for leaf node, so P minus 1, assume that keys as well as, okay, P minus 1 record pointers, record pointers, and only one block pointer is required for the leaf node. So for internal node, because there is no record pointers, the order of B plus tree internal node much more than B tree internal node. And for leaf node also, so instead of the P minus 1 P block pointers, here only one block pointer is there. So because of less block pointers, the order value of the leaf node also more than the B plus tree node. So overall what we can say, the if block size allocated for node is same, if block size allocated for node is same, the order P of the B plus tree, assume P1, order P of the B tree P1 and B plus tree is P2. Okay, so then the B tree order is too small compared to the B plus tree order. Okay, because of less degree, less number of keys and more levels. Okay, so if block size allocated for B tree and B plus tree is same, then B plus tree IO cost is less. Okay, so B plus tree IO cost is less. This is the one statement. But in case if we allocate the same order, okay, if we allocate the same order, so there is one advantage of B tree. Okay, so there is no repeated keys. Okay, internal node keys separate from the leaf node keys, but whereas in B plus tree, every key of the internal node also must be stored in the leaf nodes. Because of repeated keys, it may take the more levels, it may take the more access cost. Okay, so if order value if same for both the trees, if order value is same for both the trees, B tree access cost is less. So both are complementing each other. Okay, if block size allocated for node is same, then B plus tree runs efficiently. Okay, if order of the node if given same for B tree and B plus tree, B tree is runs efficiently. Okay, so A and D is correct answer to this question. Right. So that note is given here. Solve this question. Schedule is given, which is true. Schedule S is irrecoverable. Schedule S recoverable but not cascadeless. Schedule S is cascadeless but not strict recoverable. It's a strict recoverable schedule. Right. Make it fast. 1 minute. Anuj saying B. Mansi Ranjan. Very good. right? Okay. See, if you observe these things in this irrecoverable, okay, so if one transaction writes the data, if other transaction reads the updated value, okay, so the transaction who performs this dirty read, if committed before, then it's irrecoverable. Okay, so if transaction who performs dirty read, if delays the commit until other transaction who writes the data, okay, either committed or rollbacks, then it's a recoverable. If no uncommitted read, okay, then cascadeless recoverable. If one transaction writes until commit or rollback, no one is either reads or write, then it is strict recoverable, is the basic definitions. If you observe all these irrecoverable or recoverable or cascadeless or strict recoverable, okay, so all these are starts from a write operation, okay, after write operation only. Okay, so whatever the testing means in the recoverability classification, so before write, if any transaction if performs the read, and those reads are not going to be effect for these protocol conditions. Okay, so in case if any initial reads are there, we can simply ignore them. Okay, we can ignore the initial read. These all initial read not causes any violation to these protocol conditions. So until this, we can ignore those initial reads. Let's see the strict recoverability is true or false. T1 writes the data, but after that no other transaction reads. Okay, so then it is not violate the strict recoverability. T3 writes the data before, so T3 writes before commit or rollback. Okay, T2 is reads not allowed in the strict, it's the dirty read, it's not allowed in the cascadeless recoverable. So to get the recoverability, T3 should commit before the T2, so T3 only committed before T2. Okay, so it is a recoverable schedule but not cascadeless recoverable schedule. Okay, so the testing of strict recoverable, cascadeless recoverable, these things also one other important, right? So just recollect it. Okay, so these four definitions, just recollect it once. Okay, so the irrecoverable condition or recoverable condition or cascadeless recoverable condition or strict recoverable condition, so all are after write operation only. Okay, so write read and again write read and commit order should be followed, and if one transaction writes until commit or rollback, no one should allow for read. If one transaction writes until or commit or rollback, no other transaction allowed either read or write. Okay. So let's move to the next question. Wait die protocol. Okay. So wait die protocol and wound wait protocol. Okay, wait die and wound wait protocols prevent deadlock. Wait die and wound wait protocol prevent starvation. Wait die and wound wait protocol guaranteed for serializability, and wait die and wound wait protocol guaranteed for strict recoverability. Okay, so it is multiple selection question. Mansi says AB first. Yeah. So just check the definitions of these two protocols. Okay, so briefly check the definitions of these two protocols. So wait day protocol. Actually, these are deadlock and starvation prevention protocol. These are deadlock and starvation prevention protocol. Okay, by using lockings as well as timestamp. Okay, so deadlock and starvation. If timestamp value, TS means timestamp value of TI is less than the TJ. Okay, it means TI is older transaction and TJ is younger transaction. Okay, TI is older and TJ is younger. Okay, so first term is wait here. First term is wait here. So here older transaction allowed to wait for the younger transaction. Okay, so if TI required, older transaction required resources holded by TJ and TI allowed to wait. So older transaction allowed to wait for younger transaction. The second term is die. Okay, so if younger transaction required resource which is held by older transaction. Okay, if younger transaction required a resource which is held by older transaction, according to the protocol, roll back this younger transaction. Okay, so roll back the younger transaction TJ and restart the TJ with same timestamp value. Roll back and restart the same timestamp value. Because of rollbacking, there is no chance to form cycle in the dependency graph. Okay, so if TI timestamp value is 10 and T2 timestamp value is 20 and T3 timestamp value assume 30. Okay, and T4 timestamp value assume 40. Okay, T1 can wait for T2, T2 can wait for T3 and T3 can wait for T4 or okay, T2 can wait for T4 and so on. But in case if T2 required resource which is holded by T1, okay, older transaction, younger transaction required resource which is holded by the older transaction, then it's not allowed to wait. Okay, T2 get rollback. And the advantage is T2 is rollbacks and T2 should restart, and because of rollback no cycle means no deadlock, and rollbacks with the same timestamp value. Restarts with the same timestamp value. Because of restarting with the same timestamp value, T2 is still treated as more priority than T3 and T4. Okay, so T2 can be rollback again. Okay, T2 can be rolled back again because of T1. So until completion of the T1, there is a chance to roll back the T2. Okay, but once the T1 terminates, then there is no chance to roll back the T2. Okay, so the number of rollbacks for T2 may be depending on the existence of the T1 until completion of the T1. So definitely it is not indefinite time. Okay, so there is no chance to get the starvation. So and the other protocol, just for protocol conditions also important in the examination. So the other protocol is wound wait. First term is wound is almost equivalent to the meaning of kill. Okay, so first term is kill here. Okay, that means if older transaction required resource holded by younger transaction. Okay, older transaction required resource holded by younger transaction, then so kill the younger transaction and restart with the same timestamp value. Okay, so roll back TJ. Okay, not TI here. So younger transaction only get rollbacks TJ and restart with the same timestamp value. Okay, but the second term is wait. So younger transaction allowed to wait for the older transaction. Okay, so here also there is no possibility of cyclic dependency, no chance to form the deadlock. So these two are the starvation free as well as these two are the deadlock free protocols, but these two are not meant for serializability and these two are not meant for strict recoverability, right? Okay. conflict equal conditions is, I think, not required right now. Solve this question. So consider given transaction T1 R1A R1B, T2 W2B W2A. Okay, so T1 transaction R1A R1B, R1A R1B, T2 transaction W2B W2A. Okay, if lock requests of the transaction by using 2PL protocol as per order of data items which are used in the transaction. Okay, so data item which used, A should request before B and here B should request before A. Whatever order it is used in that transaction, in the same order it should be logs. Okay, so which of the correct statement, and it is multiple selection. Okay, we'll end the session with this question. It's a good question. Okay, try to solve this question. Right? Rajan Singh AD. Okay. Please post your answers. And ACD, Mansi AD, Anuj ACD, Komal Kumari AD. Yeah. Ansuya AD, Pradeep AD. Right. See here, data items required by the transactions. A required first, then B, and T2 B required then A. Okay. According to 2PL, okay, shared lock of A and then read of A, and shared lock of B and then read of B. Here exclusive lock of B, okay, and then write of A, and exclusive lock of A and then write of A, and after read and write, then it will unlock the A as well as unlock the B, and here unlock the B as well as unlock the A. Okay. So because see, shared lock of A and shared lock of B is the requirement for T1, exclusive B and exclusive A is requirement for the T2. In case if T1 begins locks the A and then T2 begins locks the B. Okay, so then until T2 unlocks the B, T1 not get the shared lock of B. Until T1 unlocks the A, T2 not get exclusive lock of A, and it can form the deadlock. Okay, so the deadlock is possible here. Now, every non-serial concurrent execution is free from deadlock. Okay, so of course, okay, first statement is true, means second statement is false. Okay, some non-serial is forming the deadlock, means not every non-serial is going to be free from the deadlock. Okay, some non-serial concurrent execution is conflict serializable. See, here last operation of T1 and very beginning operation of T2 conflict each other. Okay, and last operation of T2 and very beginning operation of T1 is conflict each other. In such cases, other than serial, every non-serial schedule, okay, will form the cycle in precedence graph. Okay, only serial schedules are acyclic precedence graphs. Any non-serial schedule, every possible non-serial schedule, two operations and two operations, that means 4C2. Okay, total 6 schedules. Out of 6 schedules, 2 serials. Okay, so if we subtract those 2 serials, remaining 4 non-serial schedules, all 4 non-serial schedules cycle in the precedence graph. Okay, some non-serial schedule is conflict serializable is false. Okay, out of this 4 non-serial schedule, every non-serial schedule fail for the conflict serializability. Okay, so A and D is correct statement for this given question, right? So C is not correct. Right. Okay, just little extension, we'll close the session, little extension to the previous question. In case T1 need read of A and then read of B. Okay, so transaction T1 need read of A and then read of B, and transaction T2 write of A and then write of B. Same options. Okay, if lock requests of the transactions by using 2PL as per order of data items used by the transactions. Okay, it means same data, shared lock of A and shared lock of B. Okay, and then unlock of A and unlock of B. And second transaction, exclusive lock of A and then exclusive lock of B, and unlock of A and unlock of B. If this is the scenario, so, and options are some non-serial concurrent execution of T1 and T2 forms deadlock. Okay, so every non-serial execution of T1, T2 free from deadlock, and some non-serial concurrent execution of T1 and T2 is conflict serializable. Okay, every non-serial concurrent execution is not conflict serializable. Okay. Answer this question. Small change to the previous. Okay, so instead of read A, read B, and write B, write A, here read A, read B, A and then B, here also A and then B. Pradeep says BC. Komal Kumari says AC. Ranjan says AC. Ansuya says BC. Very good. Right. Okay. So, not forms any deadlock, and some of them can be conflict serializable. Everyone may not fail for the conflict serializability. Okay, so not forms any deadlock is a very simple reason. If T1 begins, okay, assume T1 begins the execution, shared lock of A. Until T1 unlocks the A, until T1 unlocks the A, T2 can't begin. So that means there is no chance to get the mutual weighting, okay? No chance to form any deadlock, okay, of any concurrent execution. Some can satisfy conflict serializability and some can fail for the conflict serializability. So there is nothing like every non-serial fails or every non-serial satisfies. For example, if we form the two non-serials, okay, so okay, if we write the two non-serials for T1 and T2, one allowed for conflict serializability, one not allowed for conflict serializability. Assume R1A and W2A and W2B and R1B, and this is one. And other possibility of non-serial, okay, R1A and W2A and R1B and W2B. So whereas this is also non-serial concurrent execution which is not conflict serializable, cycle in the precedence graph. This is non-serial concurrent execution, okay, which is conflict serializable, no cycle in the precedence graph. Okay, some of them, okay, some of them are conflict serializable. Okay, everyone fail for conflict serializability is false. Okay, so because obviously at least one of them conflict serializable means definitely not all the schedule non-serial concurrent execution is failed for conflict serializability, right? So B and C are the correct answers. Okay, we'll share this PDF and either in whatsoever the possible communication. So we'll share into the PDF or maybe in the description of this YouTube video. So thank you so much and all the very best. Tomorrow we'll going to be discuss algorithm gate through questions. Okay, thank you so much.